right, we'll record all this. Okay, so we just did carboxylic acid derivatives, but and we did things like you know, where this was a leaving group. And then we had and we had a nucleophile. And we did substitution reactions. I'll put a negative here so I don't have to worry about like charges. Nah, it's 2 dots. It's the lone pair. Yeah, sorry, I'll make them bigger. Yeah. So this is chapter 15, kind of in a nutshell. And so we call these carboxylic acid derivatives. These are type 1. And then they usually abbreviate it like CAD, carboxylic acid derivatives. So that's what that is. So in aldehydes and ketones, there's 2 things that are going to be really different about the reactions. 2 major things anyways. One is when you're talking about an aldehyde, you've got something like that, and I'm going to put an R over here. So R can be anything. And a ketone is what? It's R. Oh, and then another R. So I'm going to call that R prime. That's just a different R group. It could be the same thing, right? pKa's of these things are very high. So these are really bad leaving groups. And that there's no way to make them better, so they leave, so they're stuck. So a lot of the reactions that we're going to look at are addition reactions, just straight up. You're going to take a nucleophile, you're going to attack the carbon, and you're going to end up doing something like this. Or something like this. I'll cap off in just a second. I'll cap that oxygen off. Okay. And then typically it's under acidic conditions, or we're going to add an acid. So in a subsequent step, this usually comes out like as an O-. Then a subsequent step, we're going to end up protonating it. So the hydrogen will cap that off like that. So that's one type of reaction that we look at in this chapter. We don't have a good leaving group. Nucleophile comes in, it attaches itself to the carbonyl carbon, and then stays. Okay. Aldehyde pKa? I don't know. Pretty high. It's got to be up like 30 or something. And then the R prime, like a hydride, like H-, has got to be up above 30 somewhere. And then alkyl group pKa's are up in the 60s. Yeah, so they're basically not going to leave. Once you get them on there, they're stuck. So really what we're looking at is in this group, we're looking at hydrogen nucleophiles. These are hydrides. And carbon nucleophiles. So we're going to be looking at things like Grignard. So one of these this is where we start bringing a lot of the organometallic stuff in. This will be Grignard. We're going to look at another reagent. It's called a Gilman reagent. I should probably capitalize the G's. These are both names. So this is organo magnesium. This is organo copper. And then we're also going to be looking at acetylide. So like acetylenes, where you take the proton off and acts as a nucleophile. These are all reagents that when they attach, they're very hard to kick off. Acetylide's a little bit easier. Its pKa is a little bit lower. But all of these will attach and make sort of this tetrahedral intermediate, right? This is the TI, or tetrahedral product. And whether or not the reaction can reverse just depends on what the pKa of that added group is. So we're looking at hydrogen nucleophiles, we're looking at carbon nucleophiles, and in the carbon nucleophiles, we just have, there's a whole bunch of them. Let's see if I have a list of them here somewhere. Okay, so that's one way that these reactions are different. The nucleophiles that come in, they attach, and essentially they attach irreversibly. The cyanide can be reversed, but we will fix it in place. Acetylide is an irreversible attachment. It turns out the other kind of reaction we have has to do with nucleophiles like this. They're going to be, let me put a note over here, oxygen and nitrogen nucleophiles. So those would be things like with O minuses on them or N minuses. And a funny thing happens in these reactions, and it's in part because of the way we do the reactions. Okay. So what's going to happen is, again, we're going to have R double bond O like this. And then I'm going to put R prime here, and I'm going to just say R prime equals H or alkyl. So that covers aldehydes and ketones. Okay, so that's what we have. So what's going to happen in these reactions is actually going to happen in steps. But the difference in these oxygen and nitrogen nucleophiles, they can donate a second electron pair. And we're going to treat them differently, actually, because they behave differently, because nitrogen's a better electron donor than oxygen is, just because it's less electronegative, right? It's further to the left. Can donate a second pair of electrons. Okay, so I have carbon, hydrogen, and in the carbon there's acetylide, Gilman, there's a bunch of Grignard, irreversible attachments that happen, and those are straight addition reactions. These turn out to do this. You do initially do an addition reaction. And I'm going to do it with nitrogen for now. But you can do the same thing with oxygen. So this is the kind of intermediate that you'll get. And it's the nitrogen has a couple of different possible functional groups on it. And we'll talk about those. But the important thing is it has a second electron pair on it. So this is addition, all right? Because addition just means you're adding it. The second part's an elimination. And so what's going to end up happening in this elimination reaction, you have this nitrogen that's like this. I'm going to just show you like the coarse outline of the mechanism. You protonate that oxygen. And it eliminates the oxygen from the carbonyl group. Okay. And this is especially true for nitrogen, because nitrogen's a better electron donor. It's more basic than oxygen is, and so you can pick the oxygen off pretty easy. When you use oxygen as the nucleophile, the tendency to kick the oxygen off or for the nucleophile to leave is the same, because of both oxygens. So if I had at this point, brought in an oxygen nucleophile right here, the tendency would be just as great to go in the left towards the reactant side as to the product side. And the way we make it work is in this reaction, this is water. We remove the water from the system. We just boil it out. And usually it's done by boiling it out with another solvent. Okay. But you can remove that water, and then you form a whole series of compounds with nitrogen substituting the carbonyl group now. So these become this structure. Kind of missed the nitrogen there. Let me redo that. I'm trying to not take up a lot of space. Oh, I lost my R prime. That's an R prime right there. And then usually one of these R groups, so it doesn't have to be, but usually one of the R groups is a hydrogen, and we deprotonate it. One of these is usually typically a hydrogen. So these are, the top ones are addition reactions, the bottom ones are addition elimination reactions. It's similar to the addition elimination that we did. That's what the last one, carboxylic acid derivative ones were called, because you added something and then you eliminated the leaving group. Here, it's just that the leaving group is the oxygen from the original carbonyl. And this is why I don't like using slides on this stuff. There's like all this information, right? There's 27, 30 pages of notes like this. Sorry. I'll try to make it shorter. All right, so we're like half a page in. All right, so let's talk about like reactivity, and then I'm going to talk about how you make aldehydes and ketones, because that's kind of, as a review.
So would that be product in there?
Yeah, it's that kind of product, but that R group is usually a hydrogen. It doesn't have to be, but this is usually hydrogen. And so this will have a positive charge, and then you just neutralize it.
This would be like a endothermic reaction, right?
Huh?
This would be an endothermic reaction.
No, it's probably, did you say endo?
Yeah.
Yeah, that one will probably be a little endothermic. No, it's actually gonna be a little exothermic, because the nitrogen, I think, because it's the better electron donor. But I think it's going to be a little endothermic, yeah, but not a lot. And so the way we make these reactions happen is we usually remove the water as the product from the reaction, right? So they're kind of, if you don't do anything, it's stable. If you add water to it, it'll revert back to the reactant. If you take the water out, it'll form the product. Okay. So those are the two like general kinds of reactions that we're going to be looking at in this chapter. So let's talk a little bit about reactivity. And then I'm going to talk about how you make aldehydes and ketones as a review of like all the stuff that we've had in the past, and I'm going to add some stuff to it. Your book, I don't know if they have that summary. Some books do this, some books don't. So reactivity. So what we have to look at is this. We have a carbon, all right, with double bonded oxygen on it. And you have R groups. And again, this is alkyl. Well, actually, let me draw two separate ones. Just, I'll make it a methyl group. That's it's called a methyl ketone, but it's a ketone. And then I have, underneath it, I'll draw the aldehyde version. Like this. So what's the difference in terms of size of a methyl group versus a hydrogen? Like a methyl is much bigger, right? It's a larger group. So when you think about initially what's going on, and you're going to go to have a nucleophile, and that nucleophile is going to attack this carbon, right? You're going to form an intermediate, and the intermediate is the easiest thing to understand. So what happens in the intermediate is it becomes tetrahedral. I'll make it negatively charged so I don't have to do any protonations or anything. One of the things that'll end up happening later is we'll talk about how these, how this reactivity is important in determining what happens in a reaction. Because sometimes you'll have more reactive groups or less reactive groups, and more reactive groups might use the same reagent and go down a different pathway because the reactive functional group goes before the other functional group can go. So first thing is there's a lot of strain in this in the tetrahedral here. The strain is caused by the group, steric strain of this group. This is a larger group. So in general, the larger that group gets, the slower the reaction goes. Hydrogen small has relatively low strain. Okay. So if you're drawing a reaction coordinate diagram, it's the end of the page. Reaction coordinate diagram looks like this. So I have a reaction down here. And then over here I have energy, all right? This is the intermediate. So for a ketone, the intermediate energy will be up here, higher. And for the aldehyde, so I'll do it like this. The aldehyde will have lower energy like that, just because it has less strain in it. And so this is the intermediate. Now, there's also differences in the stability of the aldehyde and ketone. So this carbon, right, has a double bonded oxygen on it. And so it's got that electron withdrawing group on the top of it. So the way you make that carbon more stable is by providing it with electron density. So one of the things that methyl groups do that hydrogens don't is, your favorite word, hyperconjugation. So this is electron donating. And then it's through hyperconjugation. I'm just going to call it HC. And it does way more electron donation than hydrogen. Hydrogen has an electron cloud around it in principle that donates a little bit of electron density, but we just assume that it doesn't in the grand scheme of things. Like it's the lowest amount of electron donation you have. So no hyperconjugation. So what does that mean? It means that carbonyl, this is more stable. It's more stable because of the electron donating group. And the more electron donating the group is, the more stable it becomes. So in terms of energy then, the aldehydes are all more energetically stable than the ketones are from the very beginning. So that means it's the reactant energy. So this is a reactant. For the ketone is this. Nope. And for the aldehyde, because it doesn't have the hyperconjugation from that alkyl group like the ketone does, it's going to be higher in energy. So the net effect is this. This might be the activation energy for the aldehyde. This is the aldehyde pathway. But for the ketone, it's going to go like this. It starts out lower in energy and then goes to a higher energy. So activation energy is for the ketone. The activation energy for ketone is a lot higher than the aldehyde. So let's see. So in terms of reactivity, right? Aldehydes are way more reactive than aldehydes are way more reactive than ketones because of those things. And their reactivity, like in the big scheme of things, I'll just do it on the next page. The reactivity in the big scheme of things looks like this. You have acyl halides. So I'll use like a chloride, but it could be a bromide. These are more reactive, so this is the most reactive. And in part because the chlorines are more electron withdrawing and not able to donate electron density back because the orbital sizes aren't the same. Very different, okay? So that's got the most reactivity. And then the next most reactive would be the anhydrides. So this is similar to the chart that you had in your book for the last chapter. And then we have aldehydes. And then ketones. Like that. And then to the right of that, right, esters, amides. I think that's all that is to the right of it, actually. Aldehyde, ketones, esters, amides. Yeah, that's it. Yeah, so there's two other things to the right there. So it could go like this. Carboxylic acids. I left that one out. I was missing something. These are about the same as esters. And then that's the lowest are the amides. Okay, so those are the least reactive. So in terms of reactivity, that's sort of the grand scheme of things. That's how all that lays out. Okay, another thing that's important to understand about the reactivity, just in general, of aldehydes and ketones, is that they have what are called pro-chiral faces. So what that means is, like aldehydes and ketones are sp2, so they're flat, so they can't be chiral, but they definitely have sides. And when a nucleophile comes in, right, it can create a chiral center. So for example, R double bond O, R prime. So this is pro-chiral bases. This is sp2. But then when you add a nucleophile in, it's NU, not Na. This becomes chiral. So the phases are such that they're essentially the same to the nucleophile. So the nucleophile comes in and attacks from one side, can make R, it can attack the other side and make S. So what we say in terms of the faces, there are pro S and pro R faces that produce enantiomers. And generally speaking, the accessibility is exactly the same unless it's blocked by something. So you can create a molecule where it's blocked by something and then it doesn't always give you R or always give you S in equal amounts, okay? All right, so let's talk about how you make aldehydes and ketones. I'll leave that part up. And we'll start with, this is how I listed it out. So you have an alcohol. And by the way, this would be under the category, they usually call it preparation of aldehydes and ketones. So if you want to see like other ways to do it, if you look that up, you'll be like pages and pages of information. One way to do it is start from an alcohol. So alcohol, and then you oxidation, right? So that's going to be something like ROH, and then you're going to end up with a ketone or aldehyde, depending on if it's an internal, like a secondary alcohol or a primary alcohol. So a ketone would be from a secondary alcohol, and an aldehyde would come from a primary alcohol. So the common reagents for this, for primary alcohols, PCC is one of the ones that we use. If you remember that, PCC is that pyridinium chlorochromate. This makes primary, or takes a primary alcohol, sorry, and makes an aldehyde out of it. Now it can also be used with secondaries. It'll work to do either, but it only oxidizes once, okay? Another reagent that you could use, so let me give you an example structure like this. So let me do it like this. I'll do PCC, and then your outcome for that is this. It could also be like this, a secondary alcohol, PCC, and that'll give you a ketone. So basically, PCC is good for one oxidation step. On a secondary alcohol, it's a little bit easier to control because a secondary alcohol looks like this. You can't really oxidize it past that. So one of the things that people will use for this is just chromic acid. People don't like chromic acid because it's pretty toxic. So is PCC, it has chromium in it, right? That's the name. But chromic acid is abbreviated a lot of different ways. One of them is just like this.
Is that the H2CrO4?
Yeah, so they'll write it like this. They'll write it as chromium trioxide and sulfuric acid. But what that does in solution, it forms chromic acid. So they'll write it like lots of different ways. And what I always tell people to do, just look for the chromium. And if it's aqueous, has sulfuric acid in it, then it's going to be a chromic acid oxidation. Okay. So this is converts to H2CrO4. So that's the chromic acid oxidation. And this will produce a ketone. But the problem with chromic acid is if you do it with this, it'll convert it into a carboxylic acid. So it'll just oxidize it all the way. That's the, other than carbon dioxide, that's the furthest you can oxidize it and still have it be on the carbon chain. It turns out for tertiary alcohols, like this, right, there's no reaction. Because it turns out in the oxidation, it's actually an elimination reaction similar to the one that I showed you. Like we talked about the two types of reactions for aldehydes and ketones where you have addition, then addition elimination. It's similar to the addition elimination reaction where you're removing the oxygen from the carbonyl.
So does it make an aldehyde? It makes a carboxylic acid?
Well, if it's primary, yeah, it actually, it makes the aldehyde, but it doesn't stop. So this is, again, this is H2CrO4.
Yeah, you did. I think I did too. Yeah, because I thought that turned to an aldehyde.
No, if it's PCC, which is it's a derivative of chromic acid, it stops because it's actually, PCC is done without water. And it turns out the water is what helps take it all the way to carboxylic acid.
Yeah, because I did it for primary and I made it to an aldehyde.
You'll get partial credit. That's fine. Not the end of the world. Okay, so you can make from alcohols, right? They're all chromate oxidations. Oh yeah, one other I should mention that you can do is bleach. I'll put it on the left side. So it's ClO4 minus. Oh yeah, no, ClO minus. Sorry, ClO minus. Hypochlorite.
What's in R? What's in R?
No reaction.
Cool. Yeah.
But hypochlorite oxidation is just like PCC, and it's a lot more environmentally friendly. It just doesn't work real great all the time. Has to be soluble in water, for example, and then that's not always going to happen. So, all right. The other way you can make aldehydes and ketones is from alkynes. And in the reaction, what you end up doing is you do the hydration reaction. Let's write the general what's going on. And then it's usually acid catalyzed, right? And then you'll end up with an enol, and the enol converts to the keto form. So there's basically two schemes on these. I'm gonna do it like this. I'll put the C's in there, might as well. If you hydrate that alcohol, then or that carbon, right, and you form the enol there, you're gonna get this. And that converts over to.
So it does work out.
I guess.
No, my synthesis.
Oh.
Because I put HCl, so it chlorinates it to oxygens. So it did work out. Unintentionally, it worked out.
Anyways, so then you'll get an aldehyde. If you protonate this one, if you create the alcohol at this point, then your enol looks like this. Okay. And this will form the ketone. In this case, it'll be what's called a methyl ketone. There's a methyl group to the right. But if it's an internal alkyne anywhere in the middle, it will do that. If it's an internal alkyne, you always end up with two products. Sometimes if it's a symmetric alkyne, you'll get the same product twice, but it always ends up forming two. So how do you do the two different kinds, right? So do you guys remember? Yeah, so for doing this one, this is H2SO4. Water.
Hydrate.
And then a mercury sulfate.
That's for primary.
And no, that's for the bottom one. That's for the bottom one. Because this one follows Markovnikov's rule.
And the top one would just be that just happens by adding it to water.
No. It's a prime. So think about this. When you did this with it, if you do this with
Peroxide.
Hydroboration.
No, but that's the right idea, because this is anti-Markovnikov addition. You guys remember how we do that? Did you? I think you just said it.
Hydroboration.
Hydroboration reaction. You need boron.
Yeah,
Okay.
peroxide.
So this round is hydroboration. Now with alkynes, okay, so hydroboration, kind of a summary real quick. You learned it as BH3, H2, O2. Wait, BH3, H2O.
You can use or B BR2.
And I'm just trying to think what the reagents are. I hope I haven't.
H2O2.
Oh yeah. It's just it's
Just
BH3 is the first step. That's it. This is the first step. Second step is H2O2 and water.
Water.
Yeah, and so O and base. You need a strong base.
Yeah, the
Probably the
OH minus. Okay, so that's like how you would do alkenes, and you can do alkynes this way, and it still works. But if you remember in the mechanism, what's going to happen is the boron is going to add to this group here, and the hydrogen is going to add to the internal one here. And so part of the reason this works is the electronic. It's better to have a positive charge on the internal carbon rather than on the end carbon, because what you're doing is you're forming a transition state that has a partial positive charge over here. And that's why that works. That's part of the reason it works. But the other reason it works is because of sterics. And so when they do this hydroboration on alkenes, it works well because the alkene is bent and it has more stuff, has more shape to it. Alkynes are linear, and so the sterics aren't as important because it's a straight segment of the molecule. So what they do is rather than, well, they can't do anything about the sterics of the molecule, right? So they do the sterics of the reagent, and that's why they use these diisoamyl boranes, these BHR2s. Because this introduced steric interference on the reagent, so it would rather be on the terminal carbon than on the internal carbon. It's just easier for it to get to. So yeah, the common reagent, and these are alkyl groups. The common reagent that is used to substitute is there's a couple of them. It's dicyamyl. Dicyamyl. It's a weird name. Boring. And the other one that's real common is this. It's BBN9. It's this. I actually have to. I'll have to draw it. That's the only way to do it. I don't know how to explain it, but it's a ring. I might be with 9 atoms in it. Oh, and this is a boron, so it's a boron in here. The 9 is for the position of the boron that's at the top. And so basically, these are big alkyl groups. That's the bulkiness. In dicyamyl borane, it looks something like this. Oh gosh, I don't think I can draw it. They have big R groups along the sides like this, and then hydrogens like this. And so it's like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It looks like that. All right. So in the BBN9, it's just all one thing. And the dicyamyl borane, it's 2 different large alkyl groups. But the sterics of these larger alkyl groups on the boron, the hydrogen here, cause it to add preferentially to the least sterically hindered carbon, which is the terminal ones. This is how you get an aldehyde instead of a ketone. All right. Let's see.
Hold it. Yeah.
Yeah, I think I have it spelled wrong here, actually. I wrote it as diisoamyl, but it's dicyamyl. And then I don't have the mechanism. I don't want to do the mechanisms. I have the mechanisms in my notes. All right, and there's oh, we're out of time. The next one, acyl halides. and then I'll stop. This, I was making a note, so that I'll know where I'm starting. But acyl halides like acetyl chloride, carbonyl with the chlorine, can also be used to produce aldehydes or ketones.